Okay, let's start. We're going to start on the next topic. But before we start, can I just say, please, can you just keep quiet when I'm trying to talk? And if you want to ask questions, just put your hand up and just stop me at any point. But please just don't talk when there's a lecture going on. Okay. Right. Okay, I'll wait for those who are just coming in. Right, so we're going to start new chapter. We were discussing how to find bending moment, the last two introductory lectures. So that was meant to be an introduction and also revision. And you will find out now as we go on, we'll be doing the same thing for the next few lectures. We'll be using how to find bending moment to do the next stage. What we want to discuss today is what is the effect of having a beam in bending. So one of the things that would normally happen is that you generate some level of stress, so in the beam. We want to show today how we relate the magnitude of the bending moment to the magnitude of the stress that you actually develop in the beam. When we finish that, we will go on to looking at how the bending moment affects the level of deformation that you have in the beam. So we're going to start with the actual level of stress. What I would like to do today, hopefully I'll finish, I want to go through the basic derivation of the equation that relates the magnitude of the bending moment to the magnitude of the stress that you develop in the beam. When we come back on Monday, then we will now do some particular case studies so on that. So I'm going to start with what I think many of you will have done is designing for strength. And I think that is what you did in the first part. When we say we are designing for strength, we're looking at the value of stress you have in the material, and we are trying to compare the value of that stress to the strength that the material has got. That could be bending strength, that could be fracture strength, that could be tensile strength. So in this part of the course, we're looking at bending, and I'll be going through those points there. They are not in any particular order. But by the time we finish this particular topic, you'll be able to do those. So let's start by looking at what happens. So that one is what I think we all know. So we know that when we apply uniaxial load to a beam, so it can be in tension or it can be in compression. So that is what that is. So when you apply what is called a coaxial, so the load is applied along the longitudinal direction of the beam, then the beam will either increase in length if it is tension or will decrease in length if you have a compressive load. So we will not be looking at that. We'll be looking at beam where the load is applied in the transverse direction, which should be something like this, where you apply load like that. So when you hear the term transverse, means the direction is perpendicular to the longitudinal axis of the beam. When we have that, it's clear that what will happen from what we've discussed before. If you have an initial length of the beam, which is simply supported, then when you apply load in the transverse direction, the beam will bend. The beam will bend that way. So it's clear from that side is in tension, and that side there is in compression. So what that means, therefore, as we go from one side to the other, you're going from tension to compression, or you're going from compression to tension. So in the implication, therefore, is that there will be somewhere in the middle which is not loaded at all, because in order to go from tension to compression, you have to go through the point of zero. So it means you have a point where there's no load. So what we'll be showing now in our derivation, I will go through the actual derivation, is what is the magnitude of stress if we know the value of the bending moment, what is the magnitude of stress that we will have at any point along the length, at any point through the actual cross-section of the beam. So let's start with the derivation. So I want you to pay attention and just bear with me as we go through this, because it's important to know when you can use the final solution that we are going to get. So I'm starting off with a simple beam. So there, and we've drawn in the plane cross-section. So I've already explained what plane cross-section is. So I will say here, anything, if you see the word transverse, it means it is perpendicular to the longitudinal direction. So we know our longitudinal direction is the one that is along the length of the beam. Now we've applied bending moment M. So a bending moment M is applied like that, and the beam has now bent. And we can see those planes, those transverse planes, they remain plane, and that is one of the assumptions of the solution that we're going to show. So those planes remain plane, but they have been rotated. So because of the load that we have on the beam. So the lower surface is in tension and the upper surface is in compression. And the middle section where we have no stress is what we call our neutral plane. That plane there is our neutral plane. So from now on, you'll be hearing this term neutral plane. It means it is a plane along which there's no bending stress at all. So we go from tensile to compression. We have to go past that neutral section. So we want to show now is the relationship between the magnitude of the bending moment M and the stress that we develop going from the tensile to the actual compressive side of the beam. There. So are we clear about that? So if we look directly onto that, I've drawn that using a rectangular cross-section, but the cross-section can be any. For that rectangular cross-section, if you look down there from your engineering drawing course in first year, if we were to do that, we will have our neutral axis like that. So remember the coordinate y is going down like that. So this is our neutral axis. So that's the axis along which there is no bending stress. So below that, here we'll have tension based on the moment we are looking at, and here we'll have compression. So we want to find the relationship between the applied bending moment and that distance y from the neutral axis that we've got. And that's what we want to show now. So those are the two questions which I've asked here. So the first one is, what is the relationship between applied bending moment? Let's see if I can get that to focus. So what is the relationship between the applied bending moment and the actual curvature, that is the slope. So I will say here, or slope. And also what is the relationship between the bending moment and the stress that you develop within the beam. So I will state there again what neutral axis is. So the neutral axis is the axis along which there's no bending stress. So it means any line along that will not change in length. So let's look at the relationship which we want to look at. So I will show a simple beam, and I will go through the derivation. So I've got a beam of initial configuration like that. So make sure that is the bending moment. That is the bending moment M acting like that. And the main assumptions we are going to make are the ones there. The first one is what we've just shown, that the transverse plane sections before the bending, they remain plane after you've applied the load. So, and then the next one is the material is elastic. So we'll be able to apply our basic Hooke's law, which we will show very shortly. And the next one, that the deformation is very small, and then you will see that again very, very soon. And the last one is that the material is also homogeneous. So who knows what that means? Equal to zero? Okay. Right. And that is right in terms of homogeneous function, not homogeneous material. So if you heard the term that the material is homogeneous, it means that any properties of the material that you have, the properties do not depend on where you are within the material. So if I take this as a material, if I look here, whatever properties I measure from here will be the same properties I measure from here, or from here, or from here. The properties are not dependent on where you are within the main structure. So I'll put there, so properties are independent of location. So that's what we mean by that. So let's quickly go through the derivation. It should be clear. I might go a bit fast, but if it is too fast for you, just put your hand up. Okay. So but remember those four main assumptions. Plane sections remain plane. The deformation is very small. We also have a linear elastic material, and we have an homogeneous case as well. So we have a beam, a straight beam, and we've applied bending moment. So here we're looking at pure bending moment. Now it has been deflected, so that is the deformed shape. So what we want to find now is what is the relationship between the applied bending moment M and the stresses that will be developed in the beam anywhere along the length of the beam and anywhere through the main cross-section of the beam. We have assumed here that the cross-section is an arbitrary cross-section. So that could be a square cross-section, it could be an I-beam, but here we're just taking an arbitrary shape. So let's look at, I'm going to look at a small length, this length here, length EF, which is at a distance y from the neutral axis. Yep.
Can you just zoom out a bit?
What, bigger? Yeah, it goes blurred, I think. Yeah? Is that okay? Right, so I'll have to keep moving this then. Right, so let's look at that. So we have the undeformed shape to the deformed shape. So we want to find how the magnitude of the bending moment is related to the stress. We know we're going to have one side will be in tension, one side is going to be in compression. So the side that is going to be in tension is the one that is here, that is below our neutral axis. Remember, our axes are such that that is our x, that is our y. Okay? So that's the axis we've chosen. So the axis is chosen along the neutral plane. So any point below our neutral axis will be in tension. So from the one that we've just shown, and any points above it will be in compression. So we've taken a small length EF, which is at a distance y below our neutral axis. We know that's going to be in tension. So that distance y will determine the magnitude of the stress at that point. So we've now taken that, we've now zoomed it up. So this is a zoomed section of that. So what we have here is the enlarged section of that, which is this. So let's look at that. The beam has bent, we know that, and because of the bend, the radius of curvature is r. So that's the radius of curvature of the neutral axis. So the length EF, which we chose before the load is applied, has now gone to length E prime, E prime and also F prime there. So now we want to find what is the stress. along that length. So we know that the length has increased because that is the side we have some tensile load on. We want to find what is the increase in length. Therefore, we can find the strain. If we know the strain, we can find the stress. So let's look at what is the strain we have along line A prime and also F prime. So I'll go to the next page, and I'm going to show the same diagram again because that's the one that we need. So our aim is to find the strain along the new length. So I'll put here, so old length is EF, and that is along our neutral axis. So because at a distance y from the neutral axis, and the new length is A prime, F prime. We know the new length has now increased a little bit. So we want to find what is the strain. So what's the strain? So the strain along X, remember our X is along the length of the beam. So the beam, that small element has been increased in length along the length. So if you want to find the strain, so what is the definition of strain from what you learned from your first year?
Is the difference in length divided by the original
Length. So we do it. That's good. Thank you. So we'll say change in length all over the original length. So if we were to look at that, so the new length, which is along this particular arc, so E prime, F prime, so we can show that that is R plus Y times d theta. So the length of an arc is the magnitude of the radius multiplied by the angle that you have between them. Yeah. And the old length is R d theta all over R d theta. Sorry, what? Which one? This one? All of that. So what we are trying to do is to find the length of an arc. If I do that, if that is theta, and that is R, for example. So you want to find, let's say that is AB. You want to find what is the length of the arc AB. So and I hope that arc AB will be R. Sorry, that's theta, R d theta.
So are we looking for a change in the horizontal or the vertical direction then?
No, we are looking because it is this length that we are looking at.
Yes, so that would be like
horizontal. Yeah.
But the angle will determine the vertical.
Yeah, remember, let me go back to the diagram. So what you have here, the beam was initially straight, okay, and you apply your load, and the beam has now bent.
Yeah.
So you are changing the length along here. So, but you then ask the question, so what is the magnitude of the change in length? The magnitude of the change in length depends on where you are in the cross section. If you are way down here, it changes more than you will be if you are right up here. So we've chosen a particular distance from the neutral axis, y, and we want to find out what is the change in length at that point. So the original length. In which diagram? This one? This one. Yeah. So the original length is the one along the neutral axis there. Because the beam was straight before. Yeah, is that clear? Maybe it's not clear to you. So if you look at that beam is straight before. So if you draw that vertical line and that vertical line, so this line CD is the same length as EF, it's the same length as AB, the same length as GH, because they are straight. But once you've applied your load, then they will all stretch by different module. And what you're looking at is what is that stretch, depending on where you are in that particular cross-section that you are looking at. Okay, so I hope that's okay. So that's the strain. If you open up that bracket, so we'll have R d theta minus Y d theta minus R d theta all over R d theta. And that will give us the strain, so at a distance y from the neutral axis, so as that. So remember, our coordinate y is 0 at the neutral axis. Neutral axis is the base. So when y equals 0, then there is no strain. That is the definition of your neutral axis, because neutral axis does not change in length. So if y is positive, that is you are below the neutral axis in this case, then you are increasing the length of the beam. If y is negative, you are above the neutral axis, you are decreasing the length of the beam. So we have the stress in terms of the distance y, but it doesn't allow us to find, sorry, we have the strain, but it doesn't allow us to find what the strain is in terms of the bending moment, which is what we want. Because what we know is the value of the bending moment. So we want to find what is the strain we will have in terms of the bending moment, what is the stress we will have in terms of the bending moment. So the next stage is to do that. But because that is the only stress we have, we know from Hooke's law,
You might just follow up just for 5 seconds.
which one?
To the left.
Yeah. So we know from first year one-dimensional Hooke's law that you've done that sigma equals Young's modulus times strain. So I can now say sigma x and also strain x. So if I know strain x, I can find the corresponding stress. So with that, because we know that strain x is y over r, it implies that that strain x is e y over r. So now I know what the magnitude of the stress will be at any distance y from the neutral axis. But I still don't know what that is in terms of the load. So the next stage now is to show what it is in terms of the load. We know it is changing as y is changing from the neutral axis from the base to the top. So let's see how we relate it to the value of the applied load. So I'm going to draw the typical cross-section. Let me just take a cross-section like that. Let's just say. So I'm going from the top of the beam right to the base. And my neutral axis is somewhere there. My y is measured downwards, positive like that. That's it. Right. So my y is measured positive downwards like that. So I know the stress is changing linearly with y. So where y has got the maximum value, so I'll have tension and compression. So I'm going to draw that line like that. So we know here it is being stretched. And at the top, it is being pushed in. So here is compression. And below is tension. So if we take any particular cross-section anywhere along the length, and you go from the base to the top, you'll be going from tension to somewhere that got a compressive load. And there is no stress along the neutral axis, so that is 0. But, so, I'm not sure what you did in your first year, but let me go to this. So what we normally have, based on the concept of equilibrium, remember these are main internal stresses. That is sigma, which is positive, and that is sigma, which is negative. So with that, we now ask the question, but we are not applying any stress along the length of the beam. We are not pushing the beam in. So we're not applying tension. There's no load that is applied along the length of the beam. We are trying to bend it, but we are generating some stresses along the length of the beam. The concept of equilibrium says that the internal stresses must be in equilibrium with what you apply. So the internal stresses must be in equilibrium with whatever you are putting onto it. But we are not applying any load along the length of the beam, but we are generating some stresses along the length of the beam. But the stresses we are generating is not uniform. It is changing from tensile to something that is very compressive at the other end. So we now want to make sure that we satisfy that statement there, that when we sum up, if we sum up the net force acting across the whole cross-section, we must get 0 because we are not applying any load along the length of the beam. So now I have the stress. So how do we convert stress to a force? Multiply by the area. So great, thank you, that's great. So what I want to do now is that I know that I have a stress which is tensile here, stress that is in compression there. We just take an arbitrary small section. If I take small section there, which I call dy, okay? So I know I'm going to have a stress along that length of dy. Remember, that is along the whole cross section. The cross section can be rectangular, it can be an I-beam. But so we basically look at that, and I ask the question and say, what is the net force on that small length there? This net force on that small length will be sigma x multiplied by the area of that small length, which I will call dA. And that will be the net force on that small length. Let me call that dF. Okay. But that is just a small length, so we then need to go, we need to sum it up from the bottom right to the top and make sure that that is 0 because we are not applying any load along the length of the beam. What that indicates, therefore, is that if we now do that, so that will have to be 0. Yep. Do we agree? Yep. But my dA is the area of that small material there. And that small area, we can show that it is dy multiplied by the cross-sectional area. So if the beam has got a rectangular cross-section like this, that dA there will be this. Okay, so if that is what we have, in order to make sure that we satisfy the concept of equilibrium, because our solution must ensure that we do have that. So we now show that particular integral that we've got. Which one? Okay. So let me do that in a clean sheet. Maybe that's better. Right, so we have a cross section, which is like that. The neutral axis is in the middle. So the stress is changing from being tensile to being compression, like that. So that is tensile, that is tensile, that is tensile, that is tensile, that is compression. So that is our stress. So that is the stress along the length of the beam, acting along the length of the beam. But we have not applied any load along the length of the beam. We are only trying to bend it. So, but we are generating stress along the length of the beam. In order to ensure we have equilibrium, because any internal stresses you develop must be in equilibrium with whatever load you are applying on the structure. So we then need to find what is the net force that stress variation will generate. We'll take an arbitrary length like that. We call that is dy at a distance y from here. Yep. So we want to look at what is the net force from there. So we'll say the net force which you all got right is that sigma x is the net force on that small section that we've taken. And to ensure that we have equilibrium, that has to be 0 because we are not applying any load along the length of the beam. But our sigma x, which we've just shown that sigma x is modulus times y over r dA has to be 0 because that is our sigma x, which we've just shown. The modulus does not change. That is constant for the material. The radius of curvature of the bend does not change. That is a constant. Our coordinate y can change depending on where you are within the section that you are looking at. It goes from being positive to negative value. If we were to do that, we can now say that E over R, integral of y dA equals 0. If modulus does not change, and that does not change, the only thing that will have to be 0 is that one. So that will have to be 0 to make sure that we satisfy the concept of equilibrium. And that is what is on the next slide. So which I will just show. Are you okay with that now? No?
Can we go back to the previous paper, please?
Which paper?
The previous one.
I don't know which one you're referring to. This one?
Yeah, can we go further down?
This one? Yeah, that's what I've just written now.
Yeah. What does dA equal to dy multiplied by dA? Why there is, so we calculate the overall area, like the total area?
Yeah, okay, maybe. If you take this as your beam cross section, okay, so maybe let me draw it here again. So we have a beam, which is like that. That beam has a cross section through here. Let me say the cross section here could be rectangular, could be circular, it could be an I-beam. Yeah. So that area is the area of this, or the area of that, or the area of that, because you are looking at the load that cross section will take.
And for dy?
Yeah.
Yeah, and dy, what does it mean?
So if I take the rectangular cross section, you have your neutral axis like that. You have a small section like that, which is your dy. So the area you are looking at will be, if this is B, will be B times dy. That will be our dA. Okay. Okay, so let's quickly go on. I want to make sure we get this. So the first thing we've just shown is that we can find the stress, we can find the strain, but not in terms of the load. We've applied the first concept of equilibrium, and that has shown that this first moment of area will have to be 0. And if you've done the concept of centroid, which I will explain on Monday, and that basically shows that the centroid and the neutral axis will be the same for pure moment. Centroid and neutral axis coincide. So that's the first one, but we've not got what we want. What we want is to be able to find the stress in terms of the applied bending moment, So the next one, which we're going to do, I'm going to draw the particular cross-section again, which is that. And it is being bent. So therefore, tensile at the bottom and compression at the top. We have tension, 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 and compression, compression, compression. That is negative, and that is positive. And Y is measured downwards. Remember what we said, that whatever stresses that you develop must be in equilibrium with whatever load you are putting onto the structure. We are applying pure moment, not any tension force to the structure. So therefore, any moment that is generated by this stress must be in equilibrium with whatever you put onto the structure. Let me see if I can find it. So if I look at, again, at a small section, small length, distance y, and dy. So that will have a net force there, which I will call dF. And we've already said what that net force is. So we can write that. We'll say that force is sigma x. Sigma x dA is the small force that you have generated there. So our delta F is sigma x times the area of the cross-section. But that will have a moment about the neutral axis. And what will be the moment about the neutral axis? What is the moment of delta F about the neutral axis?
0.
Sorry?
0.
0? Okay. Maybe I just ask, so how do you find the moment about a point? How do you find the moment of a force?
Well, moment depends on the distance. So
Depend on the distance. So what's the distance of F from the neutral axis?
dy.
Why? So our neutral axis is here. F is acting at the distance y from it. So the small moment that is generated by the internal force, there will be y times sigma x times dA. And that moment will depend, as you can see, depend on where you are from the neutral axis. So that distance y. But because sigma x is changing along the whole cross section, so if we sum up all that bending moment, it must equal what we are applying to the structure. And that concept you will continue to get in your third year, so when you do the next course on this. So the net effect of any internal stresses must be such that it is in equilibrium with what you are putting onto the structure. So what we are not saying is that if we integrate that, so if we integrate y sigma x dA, it must equal whatever moment that you are applying to that beam. We know what sigma x is. We've just shown that sigma x is E y over r. If we put that in, then we will end up with that. So that now will allow us to relate the load, the bending moment that we have, to the magnitude of the actual curvature, which is now given as that. And the second moment of area, which is what I think we'll be discussing later, is given by that. So I'm nearly at the end of the derivation. Okay, so I'm glad we'll get there. Now we have two equations that relate the magnitude of the curvature. Remember, that is the curvature of the neutral axis. That is the bending moment wherever you are. E is the modulus. I is the second moment of area for the particular cross-section that you are looking at. So if I take that together with the one which we showed earlier, let me see if I can just find that. And this one, 2.2b, you will see our final set of equation, which is the one that we need. So that is the only derivation that we need. So if I just rewrite that, so I will say from 2.2b, which shows that E over R equals sigma x over y. Remember, we are trying to find sigma x is the stress on the beam because of the bending. That is what we are trying to find. And we know the value of sigma x depends on how far you are from the neutral axis. And that, how far you are from the neutral axis, is our y. Okay, so that's the first one. And the one that we've just shown here from 2.3a, which is E over R equals M over I. So we have two equations which give us what modulus over radius of curvature is. So then we can combine them, and what is called the standard bending equation is that the sigma over y equals bending moment over I equals E over R. Now you see, so that is the first equation that you have on the 3-page formula sheet that you've got. So this is the one that we're now going to start to use. I will just explain what it is. So it's a beam with a particular bending moment, M, which we will know depending on which part of the beam that you are looking at. I is the second moment of area. We're going to show what that is much later. E is the Young's modulus of the material that the beam is made of, and R is the radius of curvature of the beam. Of the beam. Sorry?
Radius of what?
Is the radius of curvature, because the beam is bent.
Oh, you mean at a certain moment, the certain part of the.
Yeah. And sigma is the stress that the applied bending moment is generating, but that stress will be evaluated at a particular distance from the neutral axis. So if I want to find the value of the stress at a distance of 1 millimeter from the neutral axis, then my y will be taken as 1 millimeter. And the units here should be standard. I would suggest you use standard SI unit. Stress in Newton per meter squared. Y is length, should be in meters. M is in Newton meters. I is meters raised to power 4. Modulus is Newton per meter squared. Radius of curvature is in meters. So are we clear? So from now on, this is what you're going to see us use. So, but you know where it is from. The main assumption we've taken, which everybody to know, is that it's based on bending. Plane section remain plane. Material has to be linear elastic. Properties have to be homogeneous. So, and we're looking at very small deformation. So I'm going to end today. I think we have 5 minutes. Have you ever calculated second moment of area before? Yeah? Yeah? Great. All right. That's good. So we'll be using this very on Monday. So the second moment of area that we've just shown is the moment of area through the neutral axis. But sometimes the second moment of area, we want it along a different plane. So if I know what the second moment of area is along the neutral axis, and we want to find what is the corresponding second moment of area along this line there. The neutral axis is at a distance b from the one that we want to use. And what is called the parallel axis theorem, because the two lines are actually parallel, we'll say that the second moment of area along the new line is the second moment of area through the neutral axis, which we will know, which we can find, plus the area of the cross-section times b squared. And that is also in the formula sheet. If you've already downloaded the formula handout before today, you might want to correct that. I'll put in the new one. I think I missed out square in that one. You might want to add that to it. Okay, so let me summarize. I want to stop here because on Monday, I'm going to do different cases of how to find second amendment of area and also how to use this. So I want everybody to leave here with one single message, that you can find distress that is developed in a beam, in bending, at any location in the beam. Okay. And to do that, what you need is this. You got to be able to find the magnitude of the bending moment where you are, so in the beam, and therefore you can now use this. We will do that on Monday. Okay, so I'll see you on Monday. So the first tutorial starts next week, and you should be able to do questions 1, 2, and 3, plus question 4, 1.